So I teach a case called Maximilian Untergrundbahn, which is a nice application of the Lagrangian technique. But I wanted to produce this video to provide a bit more detail on some of the key fundamental concepts that lurk behind that case. So this is a presentation about maximization subject to constraint. It's a key part of consumer theory in economics. An overview of this presentation is that we'll look at indifference curves, we'll look at budget constraints, and then we'll see how we can solve the consumer problem by putting indifference curves and budget constraints together via the Lagrangian technique. So we'll look at indifference curves first, and let's imagine that we have two different bundles of goods. So bundle 1 has 14 units of good A and 66 units of good B. Bundle 2 has 43 units of good A and 49 units of good B. And what we're trying to do here is make a comparison as to whether or not a consumer is likely to favour one bundle more than the other. And it's difficult in this situation because we can see that bundle 2 has got more units of A, but it's got yet less units of B. So it's inconclusive as to whether or not we're likely to prefer one or the other. But we can make three statements. We can say that the consumer is either going to favour bundle 1 over bundle 2, or they're going to favour bundle 2 over bundle 1, or thirdly, the only other possible outcome is that these two bundles are equally preferred. And this is what we're going to look at in more detail with a slightly more precise and concise analytical representation of consumer preferences. In particular, we're going to make a couple of assumptions. We're going to assume firstly that we have completeness, which means that consumers can rank all possible combinations of goods and services. We're going to assume transitivity, which says that if A is preferred to B and B is preferred to C, then A must be preferred to C. If we replace these letters with heights of people, all we're saying here is that if Alan is taller than Brian, and if Brian is taller than Craig, then Alan has to be taller than Craig. We can think about what would happen if we didn't obey the laws of transitivity. Let's imagine that you, as a typical consumer, say, I value good A rather than good B, and I value good B rather than good C, but in fact I value C rather than A. If this was the case, and if you started off with good C, then you'd be happy to swap it for good B. You'd also be happy to swap good B for good A, but now you've got A, you'd also be willing to swap this for C, and you'd be back round to where you started. So you'd be willing to make multiple trades even though you end up with the same good, and economists refer to this as a money pump. So we expect transitivity to hold, and then finally the third assumption that we're going to make is more is better, which means you'd always prefer more of a good than less of it. So we can make an assumption that we can store things, or that we can just dispose of anything that we don't happen to want. And so it's a reasonably trivial assumption to say that if we have two bundles of goods, for example, if we've got 20 units of A and 85 units of B, and we've got 20 units of A or 80 units of B, then in this case we'd definitely prefer bundle 1 because we've got the same amount of A, but we've got more of good B, and more is better. Using these postulates, we can depict the consumer's preferences on a simple graph. This graph is showing units of good A and good B, and let's start off at point 1, which was our original bundle, which had 14 units of good A and 66 units of good B. Now notice these dotted lines which demonstrate the more is better assumption. Any combination of A and B that's to the left of the vertical line has less of good B than bundle 1. And any combination of A and B that's below the horizontal line has got less of good A than bundle 1. So we can say that any combination that's to the left of the vertical line and below the horizontal line makes us worse off. So we can look at bundle 2 here, which has got less of units A, less of units B. It must be less preferred than bundle 1. Similarly, bundles that are to the right of the vertical line and above the horizontal line make you better off. For example, anything in this quadrant in where it says number 3 is going to make us better off than at point 1. But the really interesting thing is going to be what happens in this southeast quadrant and what's going on in this northwest quadrant. So we know that anything in part 3 is going to be better than 1. 1 is going to be better than anything in part 2. But it's these issues where we have trade-offs that are going to be particularly important. Now, if we have a list of bundles, and this covers all possible bundles, and if consumers know their tastes, in other words, this is the completeness assumption at work, then if we move from bundles that we know are less preferred and end up towards bundles that are more preferred, there must be at some point a bundle that we've passed through which is equally preferred. So for example, let's consider bundle 4. At bundle 4, this is the original comparison that we were making. Let's imagine that we have 43 units of good A and we now have just 49 units of good B. And let's imagine that at bundle 4 we have exactly the same utility as at bundle 1. This point here, point 4, is exactly the right amount of additional units of A to compensate for the fact that we've got less of good B. We can say that the consumer is indifferent between bundle 1 and bundle 4. Now there must also be something in the southeast quadrant that makes the consumer indifferent, so we're going to label this as bundle 5. And if we can say that the consumer is indifferent between bundle 1 and bundle 4 and between bundle 1 and bundle 5, then they must also, due to transitivity assumptions, be indifferent between bundles 4 and 5. So what we have now is 3 points, point 1, point 4 and point 5, which the consumer is equally happy with, and if we join these points up, then we create an indifference curve. Our definition of an indifference curve, therefore, is a set of bundles for which the consumer is indifferent. Every single point on an indifference curve shows some combination of A and B that the consumer is indifferent between. Now, this is a theoretical claim, since indifference curves can't really exist in the real world. There's a famous story of Buridan's ass, which is a donkey that's placed equidistant between two different bundles of hay. Because he can't decide which bundle of hay to walk to, he starves to death. So we can look at an indifference map here, and we can see 5 different bundles of goods, 1, 2, 3, 4, 5. And if we just look at them in isolation, it can be very difficult to tell which is going to be preferred by the consumer. An indifference curve simplifies things analytically and makes it a lot easier for us to compare bundles. So for example, with the addition of an indifference curve, we can now see that the consumer is indifferent between points 1 and 2. We can see that they prefer points 1 and 2 to point 3. We can see that they prefer point 4 to points 1 and 2. And we can make a very simple preference ordering here to say that 3 is less preferred to 1 and 2, which is less preferred to 4, and 5 is the highest preferred bundle. Now the crucial point here is that there is an indifference curve for every bundle of goods. So even though point 5 is above the indifference curve that we've drawn, there will be an indifference curve on which point 5 is placed. It's just a higher indifference curve. The key thing for the consumer, therefore, is to try and reach the highest indifference curve they possibly can and therefore maximise their utility. So bundle 3 will also appear on an indifference curve, and there'll also be an indifference curve that picks up bundle 4. Ultimately, every single point will occupy a position on an indifference curve, and this indifference map will have infinite indifference curves along it. Key thing to note about the shape of indifference curves is that indifference curves can never cross, since this would violate the more is better and transitivity assumptions by implying that the consumer is indifferent between two bundles even if one bundle is larger than the other. Now the slope of the indifference curve will depend on the consumer's preferences regarding the relationship between the two goods. This is because the slope is telling us the rate at which the consumer is willing to trade off one good for the other. We should expect that the curve will be convex because of previous assumptions we've made about consumer choice. Recollect that goods have diminishing marginal utility, which means that the more we have of one good, the less we value an additional unit. If goods become less valuable the more we have, then as we move along the A and the B axis, because we are accumulating units of good A and good B, this implies that the utility we're getting from extra units should fall. In other words, as we move along any indifference curve, the more a consumer has of one good, the more they must be given of that good before they'd be willing to give up units of the other good. For example, if I have lots of blue pens but not many black pens, you'd have to offer me lots of blue pens for me to give up one of my black ones. In other words, if I'm up here somewhere and I'm currently consuming quite a large amount of good B relative to good A, then I'm very keen to get good A rather than additional units of good B. In other words, if I'm going to give up units of good A and receive less units of good A, you're going to have to give me an incredibly large amount of good B in order to compensate. I'm not willing to receive less units of good A unless you give me a very large amount of good B. Similarly though, if I'm up here somewhere and I'm currently consuming a large amount of good A relative to good B, then this just works in the reverse. Now that I have lots and lots of good A, I'll be willing to give up a significant amount of good A in order to receive a slightly smaller amount of good B. What we can see here is that if we don't have much of good B, then the indifference curve is going to be very steep. The more B that we have, the indifference curve is going to become increasingly flat. The slope of the indifference curve is known as the marginal rate of substitution. For a given point on an indifference curve, the marginal rate of substitution tells us the rate at which the consumer is willing to exchange the good measured along the vertical axis for the good measured along the horizontal axis. This is equal to the absolute value of the slope of the indifference curve. The formula for the marginal rate of substitution is the marginal utility of good x divided by the marginal utility of good y. In other words, the marginal benefit of good x with respect to good y. All it's saying is that we like both goods and we like variety. But then this rate depends, therefore, on the type of good that we're looking at. Our tastes matter. Let's imagine that we're looking at potatoes and rice, for example. If we've got potatoes on one axis and rice on the other, consumers' preferences are going to dictate the shape of this indifference curve because it will affect the marginal rate of substitution. James and Andrew both like potatoes and rice. But let's say James is willing to give up a relatively large amount of rice for a small amount of potatoes. In that case, his indifference curves will be very flat. What we can see here is that a very large amount of rice is willing to be sacrificed in order for a relatively small amount of potatoes. We can say therefore that James prefers potatoes. The alternative to this is a very steep indifference curve. With a steep indifference curve such as this situation, we can see that the consumer is willing to sacrifice only a very small amount of rice in order for a very large amount of potatoes. We can see that Andrew, in our example, clearly prefers rice over potatoes. Both of these types of curve are convex because the marginal rate of substitution changes as the amount of each good changes. But we can also look at some more extreme types of indifference curve. For example, let's consider the indifference curves for goods like Coca-Cola relative to Pepsi. Now, assuming that you believe that Coca-Cola and Pepsi taste exactly the same, it doesn't matter how much Coca-Cola you have in terms of your willingness to trade it off against units of Pepsi. In that case, the marginal rate of substitution is going to be constant across all units of Coca-Cola, and therefore the indifference curve is going to be a straight line. The amount of Coca-Cola that you've consumed relative to Pepsi doesn't affect your willingness to substitute Coca-Cola for Pepsi. We call these types of goods perfect substitutes. Now, the alternative is to say that the marginal rate of substitution dramatically changes depending on how much of good A and good B you've consumed. So the example here might be left shoes and right shoes. We can say that there's absolutely no point in having additional left shoes unless we also have additional right shoes. In this case, if the marginal rate of substitution changes dramatically, the indifference curves are going to be this L shape. And we can look at this in more detail. Let's imagine that we're at this point here and we have maybe one left shoe and we have one right shoe. All that we're saying is that you can give me an additional left shoe so that I've got two left shoes and I'm going to be indifferent between that situation and where we started off. That additional left shoe doesn't give me any extra utility unless I have a right shoe to go with it. So it is possible for my utility to rise, but only by acquiring more of the left shoe and more right shoes and jumping onto a high indifference curve, which would look something like this. This does violate the more is better assumption because it implies that we have this range where we only care about right shoes, or similarly this range where we only care about left shoes. But that's because these are particularly unique goods. We call them perfect complement goods. Now what we end up with here is an infinite number of indifference curves, which we can call an indifference map. The further away the indifference curve is from the origin, the greater the satisfaction, so consumers wish to be on as high an indifference curve as possible. The key question though is how can we tell which indifference curve they can attain? This is where we come to budget constraints. Our indifference curve tells us what we want, but we require a budget constraint to show us what we can have. And a budget constraint requires three pieces of information. We need to know the income, we need to know the price of good A, and we need to know the price of good B. So let's imagine that we're buying alcohol for a party. Let's imagine that our income or our budget is £100 and we're choosing between just two goods, beer and wine. Imagine that wine costs £5 a bottle and beer costs £1 a can. The question is, how much beer and wine, or what combinations of beer and wine can we afford? So if we plot on a graph wine on the y-axis and beer on the x-axis, and we can consider some various points. We can say, let's imagine that we just spend all of our money on wine, and we've got £100 and wine is £5 a bottle. That means that we can afford to buy 20 bottles of wine. At point J, we've got 0 cans of beer. We spent everything on 20 bottles of wine. And we can do the same thing for beer. We can say if we spend all of our money on beer, we'll be able to afford 100 cans of beer. We wouldn't have any bottles of wine, and we're going to call this point K. Now we can draw a line between J and K, and we're going to call this our budget constraint. The definition of a budget constraint is the set of all bundles that a consumer can afford for a given level of income and prices. Now this is an extreme position. In reality, we'd probably have a combination of wine and beer, and the key question therefore is, how much wine do we have to give up to get extra units of beer? We can think of a couple of points, a couple of bundles. Bundle E, for example, has 25 bottles of wine and 15 cans of beer. Bundle F has 50 bottles of wine and 10 cans of beer. Both of these are going to exhaust our income. They're both going to add up to £100 spent. So these are both viable options, and they both exist on the budget constraint. As we can see though, that as we move from E to F, we're going to be giving up units of wine in exchange for cans of beer. We're going to be losing 5 bottles of wine, but gaining 25 cans of beer. And it should be reasonably obvious that this ratio, therefore, the change as we move along the budget constraint, is simply the price ratio. It's the price of good X divided by the price of good Y. Any point, for example, out here somewhere beyond the budget constraint is unaffordable and unattainable. Any point such as here that's inside the budget constraint we can afford, but we're not spending all of our money, and therefore it's suboptimal. What we want to do is to be able to be on the budget constraint. We can also have a look at some of the things that are going to cause this budget constraint to change. Now this is our original situation, and just for simplicity we're only going to look at the x-axis and the cans, the impact on the cans of beer that we're drinking. And essentially two things can happen. We can either see a change in income, or we can see a change in the price of one of the goods. So let's imagine, for example, that there's a change in income and our income has risen to £150. In this case, this is going to shift the entire budget constraint. We can afford 30 bottles of wine now, or we can afford 150 cans of beer. There's no impact in the ratio of the price of wine to the price of beer. It's simply going to be a change, an increase in how much we can consume. Or let's imagine that there's a change in price. For example, the price of beer falls to 50 pence. Now this isn't going to affect how much wine we can afford if we spend all of our money on wine, but it is going to mean that we can now afford twice as much beer. So if there's a change in the price of one of the goods, then we're going to see a pivot in the budget constraint, and that's because the price ratio, which is the slope of the budget constraint, has changed. A change in income therefore shifts the budget constraint. A change in the price of either good will pivot the budget constraint. So just to summarise, the budget constraint takes the general form that income is equal to the price of good X multiplied by the amount of good X plus the price of good Y multiplied by the amount of good Y. Now you may think that this isn't very useful if it only applies to a choice between two goods. After all, consumer decisions have to take into account many more possibilities, in which case you'd need an axis for every good, and if you have 3 goods give you a plane, but any more than that will mean that the diagrams are multi-dimensional. However, we can calculate things in multi-dimensions. It's just very hard to visualize, and economists have a sneaky way of getting around this by introducing the concept of a composite good. Now, a composite good is the amount of money that consumer spends on all goods other than a specific good. So let's imagine that we need wine and beer for the party, but also somebody says we need some potato chips. In this case, we can just call beer good X, and we can define good Y as a composite good made up of wine and chips. Composite good will just be the amount of money left over having made a decision about how much beer to buy. It's the amount of money you spend on everything other than beer. So what we've done so far is we've looked at indifference curves, which tells us the maximum utility a consumer can attain. And we've also looked at budget constraints, which is to see how much the consumer can afford. An indifference curve is telling us the marginal benefit of good B with respect to good A. And the budget line shows us the marginal cost of good B with respect to good A. We can use a mathematical calculation to combine these two aspects of consumer choice to find the best feasible bundle. In other words, the highest indifference curve we can reach given the budget constraint. And the technique that we're going to use to do this is the Lagrangian technique. So the Lagrangian technique is trying to solve this consumer's problem, which is what's the highest indifference curve I can get on given my budget constraint. It has two components. It has the utility function, which is the ways in which we combine good X and Y to deliver utility. And we also have the budget constraint, which is telling us our income, the price of good X, the price of good Y. The method for the Lagrangian technique is firstly to identify all of the relevant components, so to establish the constraints that we have, the price of X, the price of Y, to find out what the income is that the consumer has, to understand the utility function. Is then to write down a Lagrangian equation. The general form of a Lagrangian equation is that the Lagrangian is the objective function plus lambda multiplied by some constraint which is set equal to 0. In our case, the objective function is our utility function. That's what we're trying to, in our case, maximize. And our constraint is the budget constraint. Economists also use the Lagrangian technique, for example, in trying to work out how to minimize costs, given information relating to those costs, in which case the objective function is going to be a minimization of those costs. Having written down the Lagrangian equation, the steps are to differentiate that Lagrangian equation with respect to the three variables we're trying to find. We can then establish first order conditions, set those equal to 0, and then to solve those first order conditions to find the quantities of X and the quantities of Y. So I'll just walk through a very simple example here. Let's imagine we have a budget of £240 to split between DVDs and magazines. A DVD costs £10 and a magazine costs £2. If your utility function is U equals to X times Y, what's the best feasible bundle? So we'll follow the step-by-step process. This is the general form of the Lagrangian. In our case, our objective function is to maximize utility, which is just simply X multiplied by Y. And we know that the budget constraint is going to take the form I minus PXX minus PYY. In our case, the income is 240, the price of X is 10, and the price of Y is 2. What we need to do here is we need to differentiate this with respect to X, Y, and lambda. Just to make it a bit simpler, I've multiplied out the bracket so that we've made everything as a function of lambda. We need to use the basic rules of differentiation here. So I also give students a handout on differentiation. So if anything that I'm about to say now is problematic, it's more to do with the calculus rather than the economics. But this is a relatively simple derivative to find. We don't have anything too complicated here. So to find these first order conditions, firstly we need the derivative of the Lagrangian equation with respect to X. This is going to be simply equal to Y minus 10 lambda. We need the derivative of the Lagrangian with respect to Y, which will be equal to X minus 2 lambda, and the derivative with respect to lambda, which is 240 minus 10x minus 2y. Just note that when we do take the derivative with respect to lambda, this should return us to our original budget constraint. In the equation, we just multiplied it by this constant lambda. Therefore, when we differentiate with respect to lambda, it should just return us to the original. Now that we've got these three equations, we can set them all equal to 0. It means we have three equations with three unknown variables we should be able to solve. If y minus 10 lambda is equal to 0, then y must be equal to 10 lambda. If x minus 2 lambda is equal to 0, then we can solve to find x equals to 2 lambda. And then we can plug those values of y and x into our third equation. We can find that 240 minus 10 times 2 lambda minus 2 times 10 lambda equals 0, which gives us a value of 6 for lambda. Lambda is not critical to what we're trying to find here. We're trying to find values of y and x, and therefore if we plug lambda back into those equations, we can see that y is equal to 60 and x is equal to 12. Now lambda is an interesting concept. It's essentially telling us the marginal utility of income, and it's doing the heavy lifting here of telling us how we can translate our budget constraint into utility. But it's not really the marginal utility of income that we care about too much now. It's just finding the optimal consumption bundle, in other words, the values of x and y. And if we look at this on a graph, we can see that we have our straight line budget constraint, which is telling us how much we can afford. There's multiple indifference curves that are each telling us how we can maximize our utility. And what we're trying to do is to find the point at which the budget constraint and indifference curve have an equal gradient. This point G star is going to be the highest indifference curve we can be on given our budget constraint, and given the Lagrangian technique we've found that x is going to be equal to 12 and y is equal to 60. We cannot achieve any higher utility than the prices and the budget that we face. This is how we maximize utility given constraints.